Hello mathematicians, this is part 2 video on the C01, the ring of all real valued continuous function on closed 0, 1. Okay. In the first part, we were discussing about maximal ideas in this ring C0, 1. In this video, we will prove that C01 and more generally C power n 01. Okay, this what is C power n 01? It is set of all n time differentiable function and the nth derivative should be continuous. Okay, such functions are called n times continuously differentiable functions. So this is a subring of C01, ring of all continuous functions, and we will show that this ring, this subring is we will show that this ring, this subring is also a this ring is also not a integral domain. Okay, so the bigger ring is not integral domain. So sometimes the subring can be integral domain. Okay, but this is not the case here. Okay, let's see. Then we look at C infinity of closed 0, 1. So this is n times continuously differentiable. So if some function is infinitely differentiable, okay, it means that class of functions for which derivative of all order exist. Okay, yeah, first, second, third in all orders. There is a different name. These are also called smooth functions. Okay, okay. Then this C infinity of closed 0, 1 is again a subring of, you can think of it as a subring of Cn closed 0, 1 or C0, 1 in doesn't matter, but this is also not an integral domain. Okay, so we're going to explicitly construct zero devices in each of these rings. It is very important problem in all the competitive exams like GATE, NBHM, CSIR. In many interviews, they ask particularly about whether these rings are integral domain or not. It is very important problem. It looks like a ring theory problem, but it requires good knowledge of real analysis. Okay. Uh, okay, let's continue. So before we start, if you like my earlier videos, if you like my teaching, please like my videos and subscribe to my channel. Okay, so let's start. Okay, so C01, it consists of set of all real valued continuous function on closed 0, 1. Now let's define C1 closed 0, 1. It consists of uh, elements of C0, 1, whichever is differentiable. Okay, one times differentiable. This one means that one times differentiable, but that is not enough. The derivative, if one times differentiable, the derivative function f prime exists, and f prime is again a function on close 0, 1 to r. That function f prime also should be continuous. Okay, basically set of all f belongs to C0, 1 such that f prime exists and f prime again belongs to C0, 1. Okay, so this is called continuously differentiable functions. Okay, this is very important point. Continuously differentiable doesn't means that you can continuously differentiate it like differentiation of all order exists. No, continuously differentiable means that it is one time differentiable and the derivative is continuous. Okay, therefore it is C1 close 0, 1. Similarly C2, so this is a 2 prime, sometime put or sometime we put C2 close 0, 1. This is set of all f belongs to C01 such that f is twice differentiable and the second derivative is continuous. Okay, so these functions are called twice continuously differentiable functions. Okay, so C01 can be sometime denoted as C power 0 close 0, 1. It consists of 0, I mean it is just a notation. Okay, okay. Then we generalize this. Cn of close 0, 1 consists of n times continuously differentiable functions. That means that set of functions in C0, 1 such that its nth derivative exists and the nth derivative is also continuous. Then we come to C infinity, set of all smooth functions. So elements of C0, 1, which is infinitely differentiable, like a derivative of all order exist. Okay. Okay. So if you notice that every differentiable function is continuous. Therefore, C0, 0, 1. So this is nothing but C0, 1. Since every differentiable function is continuous, we have this inclusion. If a function is 2 times differentiable, then it is 1 time differentiable. So we get this conclusion. So this goes like this. Finally, C infinity of closed 0, 1. It is infinitely differentiable. Derivative of all order exists. So it will be subset of all these things. Okay. So in other words, C infinity of closed 0, 1 is nothing but intersection of all this. So this should be 0 to infinity. C power n of close 0, 1. That okay. This inclusion is this intersection is clear. Now we claim that all these inclusions are proper. Okay, so let's see why. Okay. We not just claim that it is we okay let's just prove that C0, 1 is not an integral domain. Then we will show that C1 one time continuously differentiable function is not integral domain. Then we show that using that idea, we next show that Cn 0, 1 is not an integral domain. Then at the last, we prove that smooth functions is not integral domain. Okay. So to prove they are not integral domain, we will explicitly show zero divisors. Let's see. So we will be using one very important lemma that is called gluing lemma. Maybe once we know what is f of x, then we will see what is gluing lemma. So to show this ring is not an integral domain, we needed a zero divisors. Okay, recall that C0, 1 is a ring with respect to pointwise addition and pointwise multiplication that we explained with the examples in the yesterday video, part 1 video. So please check part 1 video if you want to know some basic property of C01. Now I define f of x to be 0 in the interval 0 to 1 by 2. Okay, so you see this function is 0 here, and in 1 by 2 to 1 it is x minus 1 by 2. Okay, so how do I got it is x minus 1 by 2? So this is 1 by 2. If this is 1 by 2, then what is this point in xy plane? This point is 0 comma 1 by 2. X coordinate is 0. So sorry, x coordinate is 1 by 2 and y coordinate is 0. I am talking about this point. Now this point is 1 comma 1 by 2. Okay, because x coordinate is 1, y coordinate is half. Then if you can look at the line joining 2 points 1 by 2 comma 0 and 1 comma 1 by 2, you will get you will get y minus x plus 1 by 2 equal to 0. So from this you will get y equal to x minus 1 by 2, but y equal to f of x, because the y axis we always take the image. Okay, so y equal to f of x, so we get f of x equal to x minus half. That is how we got this x minus 1 by 2 by using the line joining 2 points formula that we learned from the school. Okay. Okay, so now if you look at this function, here it is 0, then it is increased up to half. This is half. Okay, now let's similarly, now we claim, okay, so if you look at this function, it is clearly continuous, but it is easy to see that this function is continuous. That is very important result we are going to use to prove that this function is continuous. That is called a gluing lemma. Okay, let's see what is gluing lemma. You take x to be a topological space. If you don't know what is topological space, take x to be a metric space. Okay, or you can take x to be real numbers also. No problem. And you assume that x equal to a union b, where A is some closed set, B is some closed set. Okay. Now, f from A to y is a continuous function. Y is some topological space again. So, and g from B to y is continuous. Now, if f of x equal to g of x for all x belongs to A intersection B, then we define a new function called union of two functions. F union g of x is defined to be f of x if x belongs to A, g of x if x belongs to B. Okay. Now x equal to A union B. So in A we are defining f of x. In B we are defining g of x. Therefore this f union g is a function on x. Okay. Since f is continuous and g is continuous and f and g is agreeing on the intersection, this function union of f and g is also a continuous function on the full set x. Okay. So it is so you have A, you have B, and you have another topological space y here. So x is union of A and B. Okay, so this full union of this part is, this is what our x. Okay, now you have a continuous, this is my A, this is my B, you have a continuous function here to here, that is our f. You have a continuous function here to A to B to y, that is g, and in the common and x equal to A union B, that we have in the intersection. These two functions take the same value, f of x equal to g of x here. Then we define a function called f union g. Then that is a, so even though f defined only on A, g defined only on B, by taking union of these two functions, I mean union of the functions defined like this, you get a new function from x to y. So we are gluing the function f and g in the intersection to get a new function from x to y. Okay, so let's see how we can use this result. We define a function f1 from close 0 comma 1 by 2 to r, which is f1 of x equal to 0. Okay, now f2 from closed 1 comma 1 by closed 1 by 2 to 1 to r, f2 of x equal to x minus 1 by 2. Okay, now these two are continuous functions. Now this close 0 comma 1 is equal to close 0 comma 1 by 2 union closed 1 by 2 comma 1. Okay, and what is the intersection of these two closed set? It is just a singleton 1 by 2. So if you apply gluing lemma, so this is my x, this is my A, this is my B, this is my A intersection B, and f1 and f2 they agree on A intersection B. Okay, because at f1 of 1 by 2 is also 0, f2 of 1 by 2 also 0. Therefore, by gluing lemma, this f1 and f2 can be glued together to make a continuous function from close 0 comma 1 to r. Okay, so if you noticed, so this is our A, this is our B, and the union of the function is defined like this. Therefore, by gluing lemma, this function is continuous. Okay, so of course you can see from the graph it is continuous, but if you need to prove it rigorously, this is one way of proving. Even though this function is easily seems to be continuous, in the when we look at the c power n close 0 comma 1, this lemma will be very useful, that we will see next. Okay, anyway, this is one function which is continuous. Similarly, we look at the g of x, defined by g of x is like this. From, so this is again 1 by 2. In 0 to 1 by 2, I take 1 by 2 minus x. Okay, so 1 by 2 minus x is this function, and 1 by 2 to 1 I take 0 function, so that the graph is like this. Okay, now if you together look at these two functions, if at some point this function is non-zero, then this function is 0 there. If this function is non-zero here, but at that point this function is 0. Okay, so if you calculate fg of x, what is the definition of fg of x? That is f of x into g of x, and x you take any point in close 0 comma 1, either this will be 0 or this will be 0. Therefore The product will be 0 for all x belongs to close 0 comma 1. Okay. Therefore, this f is a non-zero element in c 0 comma 1, and because it is not a zero function. Okay. Similarly, g is also a non-zero element of c 0 comma 1, but their product is 0. Therefore, these two things are uh, zero divisors. Therefore, c 0 comma 1 is not an integral domain. Integral domain means it should not have zero divisors, but this ring c 0 1 has zero divisors. Okay. So let's move on to c1 close 0 comma 1. Okay. Now we claim that this is also not integral domain. So you look at we use the same idea, but the function we modify a little bit. Okay. So f of x equal to 0 again in the interval 0 to 1 by 2, then x minus 1 by 2 the whole square. Okay. If you look at f in the C01 case, it is x minus 1 by 2. Now we are increasing the power x minus 1 by 2 the whole square in 1 by 2 to 1. Okay. Now we claim that this function f of x is an element of C prime 0 comma 1 or is C1 0 comma 1. That means that this function should be differentiable and its derivative should be continuous. Okay. Now, if you look at this closed 0, open 1 by 2, here it is 0 function. Therefore, f of x is differentiable there. Similarly, if you look at open 1 by 2, comma closed 1, this is this function x minus 1 by 2 the whole square, which is a polynomial. Therefore, it is differentiable. Therefore, only at the point 1 by 2 we have to check whether this function is differentiable or not. Okay. So we calculate the left derivative and the right derivative. If they are equal, then the function is differentiable at the point 1 by 2. Then the function will be differentiable everywhere, because in the other points we already shown the derivative exists. Okay. So let's look at the left derivative at the point 1 by 2, f prime of 1 by 2 minus. So what is the definition of f prime of 1 by 2 minus? Limit h tends to 0 minus f of 1 by 2 plus h minus f of 1 by 2 divided by h. This is the definition of left derivative. Now, h is approaching 0 from negative. Sorry, h is approaching 0 from left side. Therefore, h is negative. Okay, that's what it means. If h is negative, then 1 by 2 plus h will be strictly less than 1 by 2. Okay, therefore, if 1 by 2 plus h is strictly less than 1 by 2 means this quantity will belongs to this interval. Therefore, uh, this value is 0. Okay, because because h is negative, therefore 1 by 2 plus h will belongs to this interval. Therefore, this value is 0. F of 1 by 2 is already 0 by definition. Okay, you put 1 by 2 here or 1 by 2 here, both the value will be 0. Okay, so 0 by h, the value is 0. Okay, numerator is 0 means we don't need to apply the limit, it is just 0. Therefore, left derivative is 0. Why left derivative is 0? Because I mean, uh, it is exact kind of, if you draw anyway, it's fine, it is 0. Let's calculate the right derivative. So I mean, left derivative is 0 because this is basically kind of, it's coming as x-axis. So yeah, it is derivative. I mean, okay, it is more intuitive. Let's see what is right derivative at 1 by 2. So again, limit h tends to 0 plus. It means that h is approaching 0 from right. So right side of 0 you have positive numbers. Okay. Therefore, 1 by 2 plus h now will belongs to this interval. Okay, because h is positive. Therefore, now you have to, for f, you have to use this definition, because 1 by 2 plus h is in this interval. Okay. Now, if you apply 1 by 2 plus h in place of x, you will get 1 by 2 and minus n by 2 will cancel. You will get h square. Okay. And f of 1 by 2 is 0. So, you get limit h tends to 0 plus h square by h, which is equal to 0. Okay. Therefore, left derivative is also 0, right derivative also 0. Therefore, at the point 1 by 2, the derivative is 0. Okay. Therefore, derivative exists at the all point. Also, derivative is continuous because derivative is just the zero function. Sorry, derivative is not zero function. Okay, yeah, here I have written. Therefore, f prime exists at all points in closed 0, comma 1. So, derivative is in this interval, derivative is 0. Sorry, in the in the closed 0, open 1, the derivative is 0 because it is 0 function. In open 1 by 2, closed 1, this is derivative is this function. So, we have to take 2 times x minus 1 by 2, and at 1 by 2 it is the derivative is 0, so we have taken here, okay. So, this is f prime of x. So what is this? This is the definition. This is what the derivative of f. Okay. Now clearly this function is continuous again by using gluing lemma to, because this function is continuous, this function is continuous, and both the function is agreeing on the intersection of these two intervals, that is at the point 1 by 2 these two functions are agreeing. Therefore f prime is a continuous function. Therefore f prime belongs to c0 comma 1. Okay. F prime is belongs to, sorry, f prime is a continuous function. So f prime exists and it is continuous. Therefore f belongs to c1 0 comma 1. F has a continuous derivative. Okay. Okay. Now we want to note that f double prime of 1 by 2 does not exist. Okay. Maybe that we will come back late after a while. Let's see. Now we have this f is f belongs to c1 0 1. Similarly, you define the function like g of x. Okay, 1 by 2 minus x the whole square in this interval 0. Then for the same reason, you will get this g of x. Like f, whatever we done, we do the same here. You get the g of x is g is a function. G belongs to c1 0 comma 1. Okay, and then like wherever yeah g is non-zero, f will be 0. Wherever f is non-zero, g is 0. Therefore, the product is 0. Therefore, this f and g are 0 divisors in this ring z prime of 0 comma 1. Therefore, c prime of 0 comma 1 or c1 0 comma 1 is not an integral domain. Okay. Now, if you look at this function f prime of x, we claim that you can't differentiate it one more time. Okay, let's see why we cannot differentiate it one more time. So this function, if you look at it, this is just there is a only this function is very much same as this function. Okay, only there is a 2 in front Okay, so we will show that this function is not differentiable at the point 1 by 2. Then for the same reason, that function is also not differentiable at the point 1 by 2. Okay. So basically this function has a sharpness here. So this is a sharpness. It is not going very smoothly, right? So therefore it is not differentiable at 1 by 2. But we rigorously show that this function is not differentiable at 1 by 2. Okay. So how do we show it is not differentiable? We again calculate the right derivative and the left derivative. If they are not exist, then they are not, that is not differentiable. So you calculate the right derivative like we calculated earlier. Right derivative will be 1 and the left derivative will be 0. Therefore they are not differentiable at the point. F is not differentiable at 1 by 2. So for the same reason, you take f to be this function, then f prime of x is this function. Then this function is similar to the function we just saw above. This function you cannot differentiate it one more time. Okay, f double prime of 1 by 2 will not exist. Okay, because if you calculate the left derivative and the right derivative of this function using the above technique, you will we will see that this function cannot be differentiated one more time. Therefore, this function f belongs to c1 of 0 comma 1 but does not belongs to c2 of 0 comma 1 because its second derivative does not exist. Therefore, this inclusion is proper. Okay. Okay. now we go to, now we generalize this, okay. So we claim that Cn 0 comma 1 set of all n times continuously differentiable function is not an integral domain. So by imitating the same idea, so for it for one time C1 close 0 comma 1, we had 2 here, okay. So for n time we should take n plus 1, okay. Then let me just, I'll just briefly show you, like for C1, C0 comma 1 is not an integral domain. We had a 2 here. Okay. So if it is n here, you should have n plus 1 here. That is our idea. Then if you, we can, one can prove that this f of x, its nth derivative will be exist and nth derivative will be continuous. Therefore, f of x will belongs to Cn of close 0 comma 1, but its n plus 1th derivative won't exist, because if this function, if you differentiate at the once you differentiate it n times, you will get some function like this, okay, with some constant in front, okay. So once you have some function, some linear function like this, again with some argument similar to this, will show you that the n plus 1th derivative won't occur, okay. So you try to do the same for like n equal to 3. So we just showed that C1 0 comma 1 is not an integral domain, we proved. You try to do C2 close 0 comma 1 is not an integral domain. So basically you have to take 3 here, and you prove that f power 2 exists. F second derivative will be continuous, but that derivative, the third derivative won't exist, okay. Anyway, so Cn of 0 comma 1 is not an integral domain because you consider this f of x, this g of x, then these two function will belongs to Cn of close 0 comma 1 and their product is 0, okay, because wherever f is non-zero, there g is 0, wherever g is non-zero, f is 0, therefore their product will be 0. Also this f and g, both of them, f will belongs to Cn of close 0 comma 1, but f1 belongs to Cn plus 1 of close 0 comma 1, okay. So from this we conclude that, so this n is arbitrary, n is greater than or equal to 0, therefore we conclude that all these inclusions are proper, okay. Okay, let's see, I okay, so therefore now we know that Cn of close 0 comma 1 is not an integral domain because these are zero divisors. Let's look at smooth functions, infinitely differentiable functions, okay. So now we need some different approach. We need bump functions, okay. These are all called bump functions, okay, because so this is the curve. So even though it looks like it is 0 here, it is not 0. So let's see the function first. So we define f of x to be 1 by e power x into x minus 1 by 2, okay, in the interval 0 to 1 by 2 and 0 everywhere else, okay. And then this function will be like this, at so it will have some maximum at some point here. Now this function at 0, it is 0, but it is just approaches to 0. Even though a function looks like here it is going 0 0, it is not. It is not a constant function 0 here, because I mean this values it takes is very very small. For example, you see this is 2 into 10 power minus 8. So it is such a small value. Therefore, so it is actually just decreasing, decreasing, decreasing. At 0, it touches 0. Similarly, it is decreasing, decreasing, and at 0.5 only it is touches 0. Okay. Why at 0 and 0.5 it is touches 0? Because it is e power 1 by x into x minus 1 by 2. Okay. When x tends to 0, so I mean these are all the two values. This is x can be thought of as x minus 0. So this is 0, and this is x minus 1 by 2. So this is 1 by 2 is half. Okay, so in general, if you take e power 1 by a into, sorry, e power 1 by x minus a into x minus b, if you look at this function, so in the interval open a comma b, it will be positive, okay, and at a it will touch 0, at b it will touch 0, then everywhere else it will be 0. Okay, so basically curve will be like this. So this is interval, this is a, this is b, so this is the real line. So at a it will come and I think that was sort of not a good image. So this is a, this is b, then this is minus infinity, say this is plus infinity. The curve will touches 0 at a and again touches 0 at b, then it will be just 0, but it is joined here such a way that it is infinitely differentiable at every point. Okay, okay, therefore, like, but we just want the graph in 0 comma 1, so I have drawn the graph only in 0 comma 1. So this function, like, slowly it is joining to 0 at 0.5, and after 0.5 it is 0 because of this definition. Okay, okay, so similarly we look at e power 1 by x minus 1 by 2 into x minus 1. So it will join to 0 at 1 by 2 and 1. Okay, so at 1 by 2 it is decreasing, decreasing and coming and joining to 0. And again at 1 it is decreasing and going to join 0 at so this curve will touches the x-axis only at 0.5. It just keep coming closer, closer, but it touches x-axis at 0.5 and 1. Okay, so this but the function takes very smaller value, so it looks like it is touching, but it is not. Okay, there is a small some gap here. Okay, okay, therefore these two functions are infinitely differentiable. So so you check what is bump functions. They are very important functions in uh, uh, like aerial analysis, in measure theory also. So they are all called functions with compact support because it is supported only on if you take e power 1 by x minus a into x minus b, it will be supported in the interval closed a comma b, and outside it will be 0. Okay, it is a functions with um, like compact support. They are all very important functions. Okay, so you can check in the Wikipedia page regarding its properties, bump function. Okay. Therefore, like we have an example of functions in C infinity 0 comma 1, which are non-zero, but the product is 0, because wherever this function is non-zero, there this function is 0, and conversely. Okay, therefore C infinity 0 1 is also not an integral domain. Okay, so in this one problem, one video, we have covered many results. Okay, all these things are if you look at previous year question papers, there is many problems asked regarding this one video. Okay, so please remember these results, and these functions are very important, and this inclusion, this inclusion is strict. Okay, that is also very important. Okay, so sometimes they ask why C2 of closed 0 comma 1 is a properly contained C3 of closed 0 comma 1. Find some given example of a function which belongs to C3 of 0 1 but not belongs to C2 of 0 comma 1. So that you can do by using our this we have an example of a function which is in Cn but not in Cn plus 1, right? So by choosing the n appropriately, we will have this function as an example. Okay, there is very much simpler example is there, like if you look at f of x equal to x power 1 by 2 plus n, then this function will be belongs to Cn of close 0 comma 1, but it won't belongs to Cn plus 1 power close 0 comma 1. Okay, so this is very easy to verify. You try to verify that. Okay, why it is not belongs to Cn plus. Similarly, if you look at mod x power n plus 1, but you have to change the interval to minus 1 to 1. Okay, if mod x power n plus 1 will belongs to Cn of minus 1 power 1 minus 1 to 1, but it won't belongs to Cn plus 1 of minus 1 comma 1. Okay, So you can check these results by yourself. Okay guys, so I'll stop here. If you like this video, please please click the like button, and please subscribe to my channel. Thank you.